In this video, we are going to answer GCE A-Level Chemistry Paper 2, June 2021. We will be starting with question number 1. Define the term mole of a substance. Mole of a substance. You can define a mole in this way. You can say this is the amount of substance which contains 6.02 times 10 to the 23rd specified particles. That is atoms, molecules, ions, or electrons. Let me write it there. Specified. Specified particles. I'm talking of atoms, molecules, ions, or electrons. Excuse me. So you can define a mole as the amount of substance which contains 6.02 times 10 to the 23rd specified particles. Then, the second question says 1.5 gram of ethyl ethanoate was hydrolyzed with 50 cm cube of 0.5 molar sodium hydroxide solution, and that the mixture was made up to 250 cm cube with distilled water in a volumetric flask. Calculate A, the number of moles of ethyl ethanoate in 1.5 gram, and in 1.5 gram they have given the MR of ethyl ethanoate as 88. gram. Now, in order to calculate this, you have been given the mass, and you have been given the molar mass of ethyl ethanoate. So it is easy. There is a relation which is the mass. This is the mass divided by molar mass. Mass divided by molar mass will give you the number of moles. If given the mass and you know the molar mass, you divide the mass by the molar mass, it gives you the number of moles. So it is very simple. So we can now go ahead and divide it. We can now say the number of moles of ethyl ethanoate will be 1.5 gram divided by 88 gram. 88 gram per mole. And that would give us 0.0170 moles. That will give us 0.0170 moles. Now, the B part of it, calculate the number of moles of sodium hydroxide in 50 cm cube of 0.5 molar solution. Again, there is a relation. There is a relation here. We have to have the number of moles. To have the number of moles, multiply the concentration by the volume in dm cube. Multiply the concentration by the volume in dm cube. You will have the number of moles. So if we go there like that, we will have the number of moles. The moles will be equal to concentration. Our concentration times the volume. Our volume in dm cube. Our volume in dm cube. And the concentration here is 0.5. The concentration is 0.5. 0.5. That is 0.5 times the volume. The volume here is 50 cubic centimeters. Then in dm cube, 50 divided by 1000. 50 divided by 1000, we will have 0.05. 0.05 dm cube. And this is also mole per dm cube. Mole per dm cube. Dm cube and dm cube will also cancel. So we will have 0.05 times 0.5. We will have 0.025 moles. We will have 0.025 moles. Now, calculate the percentage yield when 1.5 gram of ethyl ethanoate reacts completely with sodium hydroxide to give 0.63 gram of ethanol. You know, from all this, the first thing is you need to write your equation. You need to write your equation. And in this equation, we will have ethyl ethanoate, which is, I think, CH3. Yeah. CH2 plus sodium hydroxide. It will give ethanol plus sodium ethanoate. That will be the reaction, because they said calculate the percentage yield when 1.5 gram of ethyl ethanoate reacts. This ethyl ethanoate reacts completely with sodium hydroxide to give 0.6 gram of ethanol. Okay, we have, that is a reaction. Now, what we need to do is to calculate the percentage yield. We need to calculate it, but from the limit, from the limiting reagent, and from this, from these two substances here, we have ethyl ethanoate. It is 0.0170. Then we have sodium hydroxide. It is 0.02. So ethyl ethanoate is a limiting reagent. It will get used up first before sodium hydroxide. So we are going to calculate from here. So in that case, from the equation, you can see that 1 mole here one mole of ethyl ethanoate. 1 mole of ethyl ethanoate. 1 mole of ethyl ethanoate will give 1 mole of ethanol. 1 mole ethanol. 1 mole of ethyl ethanoate will give 1 mole of ethanol. Then the calculated moles of ethyl ethanoate, which was 0.0170. Therefore, 0.0170 moles that we calculated will give what? We don't know. Let's say it will give X. Let's say it will give X. And now, and what will be X? The X will still be X will still be 0 point, X will still be 0.0170 moles of ethanol. Will still be that for ethanol. Now, that is the those are the number of moles of ethanol. We need to calculate the mass of ethanol. So now, the theoretical mass of ethanol will be what? Now, we have a relation here. Given the number of moles, to have the mass, given the number of moles to have the mass, you multiply the number of moles by the molar mass. And the molar mass of ethanol is the molar mass of ethanol is 46. The molar mass of ethanol is 46. So the theoretical mass of ethanol will be 0.0170 times 46 gram, and that will give us 0.782 gram of ethanol. Yeah, gram of ethanol. Now, okay, percentage yield. The percentage yield is percentage yield will be the percentage yield. The formula for the percentage yield will be the actual yield, or what we'll call the experimental yield, divided by the theoretical yield or what we'll call the calculated yield, what we have just calculated, times 100. Times 100. That is what we have. That will be the percentage yield. And now, if we substitute our values here, what we are going to have will be the theoretical yield was what? The mass that was given initially is 0.63 gram of ethanol. 0.63 gram. So it is 0.63 gram divided by our calculated mass is what? 0.782. 0.782 gram times 100%. And in that case, we will have 80.56%. That is what we will have. That is what we are going to have. Okay. Once more, I said, you can only calculate the percentage yield, but from the limiting reagent. From the limiting reagent, look at the masses. I mean, the moles of ethyl ethanoate and the sodium hydroxide. You will see that the one for ethyl ethanoate is lower than that of sodium hydroxide. For that reason, you are going to calculate from ethyl ethanoate. So that is why we go ahead to write the equation. Then from there from the equation we will say if 1 mole of ethyl ethanoate can yield 1 mole of ethanol, therefore the calculated mole, which is 0.0170, will yield what? It also gave us the same amount of moles. So knowing the number of moles, to calculate the mass, you only have to multiply it by the molar mass, and the molar mass of ethanol is 46. For that purpose, the theoretical mass of ethanol will be what? Will be 0.0170 times 46. When we do that, we will have 0.782 gram of ethanol. Okay, percentage yield. Percentage yield is the actual yield, or what we call the experimental yield, divided by the theoretical yield, or what we call the calculated yield, times 100. When we do that, we'll have 0.63 gram divided by 0.782 times 100%. We will have 80.56% as our percentage yield. Let's move ahead to the next question, the C part of it. The following is a path of uranium decay. This is a path of uranium decay. Okay, you have uranium from here. You have uranium to another compound, A to B and to C. A, B, and to C. Now, identify the particles. Identify the particles emitted in step A and B. Identify the particles emitted in step A and B. Okay, it's very simple. Now you have here you have the atomic number just has decreased by 2. This one too has decreased by 4. In that case, it's an alpha particle or a helium particle. A is alpha particle. You can either write that it is 4, 2, or you can write as 4 to a helium. The alpha particle or the helium. That is it. Then B. B part of it, the atomic number has increased by 1 and the other one remained. So we call it, in this case, we will call it, this is a negative electron. A negative electron. You can either write like that. So it is, we call it beta minus. It's beta minus. It's beta minus. You can either write like that. Then 2. It is beta minus. All these we call it beta minus, or what we call a negative electron. That is beta minus. Beta minus. That is the value for beta minus. Okay. If a beta particle is emitted in stage C, give the atomic number and the mass number of the isotope X. Okay, the atomic number, if a beta particle is emitted, automatically the atomic number is going to be 92. Atomic number is 92. Atomic number is 92, and the mass number will be 234. will be T34. And this is what is happening there. This is what is happening in that thing. This is what is happening there. It is 234 into 91. This is what happened. Is 234 92 plus you will have plus that is what is happening there for you to have that. Okay. Now number 3. Okay, if the activity of this element is reduced to 25% in 48 days, what is the half-life? What is the half-life of the element? There's one thing you have to do with this. In this step number 1 in this thing is that step 1, initial mass. The initial mass was 100%. The initial mass was 100%, which was what? The initial mass was 100%, which was 234 gram. We were 234 gram. Step number 2, that's how you have to put it. Step 2, in step 2, the number of half-lives, number of half-lives in this way we need to draw a table. Number of half-lives. Okay, half-life and the mass. So at time equals to 0, at time equals to 0, the mass was 100%. The mass was 100%, and which was what? Which was 234. The first half-life, this will be halved. That is 50%, and that will be equal to what? That is 117. Then second half-life, the second half-life This will now half again. That is 25%. And 25% of this is what? Is 58. 58.5. Okay, total number of half-lives. Total half-life. Total half-life is equal to what? 2. The total half-life is equal to 2. Now, total half-life is equal to 2. Step number 3. Step 3. Step number 3. Number of half-lives equals to what? Elapsed time. The time that was given. Elapsed time or total time. Total time divided by what? Divided by the half-life. Divided by half-life. Okay. From this, we can now calculate. Our half-life. Our half-life now will be total time divided by the number of half-lives. Our half-life will now be 48 divided by 2, which will be equals to 24 days. So that is how you can calculate it. I said step number 1, the initial mass is 100%, which is equal to 234. Then step number 2, the number of half-lives. And now construct a table. Time equals to 0. The mass is 100%, which is 234. If we have the time, it will be 50%, and it will be 117. Now, after that, we go to half again. It will be 25%, and that will be 58.8, 58.5. Now, we have arrived at the time or at the percentage that was given. And the total half-life is what? 2 half-lives. Now there is a relation. The total time, half-life, and the number of half-lives. So when we are looking for the half-life, we now make this a subject, and that is what we have just done here. Our half-life will now be what? It will be total time divided by what? Divided by the number of half-lives, which is equals to 2. And our answer is 24. 24 days. It takes us to the next question. The next question, which is on the mass spectrum. The next question is on mass spectrum. The next question is on mass spectrum. So it's 24 days. It's 24 days. Yeah. Okay, the mass spectrum of a vaporized sample of chromium shows the following data. The mass of isotope is 50, 52, 53, and 54. The relative abundances are there. Calculate the relative atomic mass of chromium. There is a relation here. Know that when you are given the mass, let me say M1. This is the masses M1, M2, M3, and the relative abundances as A, B, and C corresponding to this. In order to calculate the relative atomic mass, is the mass times the relative abundance. The mass of each isotope times the relative abundance. Then a summation of all of them divided by a summation of the relative abundances. So let's go ahead. Here, this is what you are going to do. Yep. In order to have it here, the relative atomic mass is 50. It will be 50, let me say 50. 50 times 0.04 plus 52 times 0.84 plus 53 times 0.1 plus 54 times 0.02. All of this divided by 0.04 plus 0.84 plus 0.1 plus 0.02, and the final answer will be 52.06. 52.06. Okay, it takes us to the E part of it. On rates of chemical reaction, the following data were obtained from the reaction below. So now that is the reaction. We have been given the concentration of the two reactants and the reaction, the rate of reaction. Now, question number 1. Determine the order with respect to NO. In order to determine the rate, the order, what do? We have to hold this. The concentration of hydrogen, we have to hold it constant. Like this one here. We have to hold this concentration constant. And if we are to do that, this is what we are going to do. Remember that the rate equation is, this is how you write the rate equation. The rate equation is like this. The rate equation for this is, it is NO to the power. We don't know this. So now, in order to know this, we are going to calculate the order with respect to NO. So for that purpose, when we hold this constant, when we keep this concentration constant, we use this and we use this. keep the concentration of hydrogen constant and use this one, the corresponding one over here, and the corresponding rate over here. Just see how I'm going to do it. Okay. I'm using this rate equation. I want to use this rate equation here. In this rate equation, what I'm going to do is this. I put a K there at a constant. Okay. Keeping this constant, it will be 0.3 divided by 0.1. To the power, we don't know, which is equal to, on the rate, I will put 9 divided by 1. 9 divided by 1. So now, let's do this. K, that is the rate constant. This divided by this is 3. Say that it is 3 here. 3 to the power x, which is equals to 9. 9. Okay, something must happen, which is, okay, 3 to 9. We now say k to 3 to the power x, and 9, which will be equal to what? What factor can we multiply? Can we square? That will give us 9. 3. We now go into 3 square. Okay. In that other, we will have 3. Therefore, we now say x is equals to what? 2. That is second order with respect to NO. We can now come and conclude here that x, the order, determine the order with respect to NO. Second order. Since we have calculated the value of x, we now say x is equals to 2. And that is second order. We now say it is second order. Second order. Okay, the same thing. Determine the order with respect to hydrogen. With respect to hydrogen, we will have to keep the concentration of NO constant. We have to keep the concentration of NO constant. In that case, we have to keep this constant because we are dealing now with hydrogen. So now with hydrogen, if we keep that constant, what we are going to do now will be, the rate for nitrogen will be, it will be K. Now, keeping this constant for hydrogen, it will be 2 divided by 0.2 divided by 0.1. 0.2 divided by 0.1 to the power y. The other one was x, which is equal to what? The rate, the corresponding rate here will be what? The corresponding rate here will be 18 divided by 9. 18 divided by 9. Now, it is K. Eighteen divided by 9 is 2. 2 raised to the power 1 remains 2. Therefore, y is equal to what? 1. First order. We can now conclude that the order with respect to hydrogen is first order. Order with respect to hydrogen is first order. Is first order. So we can now write, if you were to write the rate expression. Write the rate expression. The rate expression after calculating the order, the rate expression for them will be, the rate expression will be the rate will be calculate the value of the rate constant. Calculate the value of the rate constant. The rate constant, from there we can calculate the value of the rate constant. The rate constant here, the value K, from here, K will be rate divided by this. So K, the rate constant K will be equal to rate which is 1. If I take 1, we will have 0.1. We will have 0.1. 0.1 mole times 0.1 again. The value of K will be 1 times So just substituting the values here will substituting the value of substituting the values here, taking the concentration and substituting here with the rate will give you 1 times 10 to the 10 1 times 10 to the third power mole cube mole per cube dm to the 9 power. So that is the value. Okay, it takes us to the the F section of the question. A solution A contains 0.10 mole of ethanoic acid and 0.2 mole per dm cube of sodium ethanoate. Give the general name for such a solution. Give the general name for a solution such as A. You know that when you mix a weak acid and its salt, it gives you a buffer solution. So the name of this is acidic buffer solution. This is an acidic buffer solution. Acidic buffer solution. This is an acidic buffer solution. Give one use of the solution A. You know that solution a buffer solution, this is a solution that can resist any addition or any, it can resist a change in pH when a little acid or alkali is added. So it is used to maintain the acidic environment. It is used to maintain the acidic environment. I mean maintaining a stable pH in a solution. I say it is used to maintain acidic environment. Used to maintain acidic environment. That is maintaining a stable pH in a solution. Then the third one is calculate the pH value of solution A. The pH value of solution A. The pH value of solution A. To calculate the pH value of solution A, you have been given the number of moles. You have been given the number of moles. Now you have been asked to calculate the pH value. So the next thing you will do will be, you write your equation. You need to write your equation like this one. You need to write your equation. When you write your equation, the weak acid dissociation to form the conjugate base, the weak acid dissociates to form the conjugate base and the hydrogen ion. Then Ka. The Ka is the conjugate base and the hydrogen ion divided by the weak acid. Now we make hydrogen ion the subject. Then we can now substitute our value. If we substitute our value, for instance, let me substitute the value here and you see what is going to be. If we substitute our value here, what we are going to have will be the hydrogen ion will be 0. That is 0.00 08 0.00 the acid was 0.10, then the conjugate base was 0.20. If we calculate all this, we will have 9.0 times 10 to the minus 6 mole per dm cube. Now, how it is, then our pH will be a negative log of hydrogen ion. This is hydrogen ion. So we now say negative log of 9.0 times 10 to the minus 6. So if we do that, what we are going to have will be minus 5. Minus 5.05. Minus 5.05. Remember, there is a minus here. So our pH value now will be 5.05. That will be our pH value. There is another method. So once more, I said when you have such equation, you need to write an equation. When you write the equation, this dissociation equation, put it there, put a Ka. Now put a Ka now. Then make hydrogen ion the subject. After making hydrogen ion the subject, now substitute the value, the concentration. Substitute the values now, the concentration that you were given. Then look for negative logarithm. From there you have the answer. Method 2, there is another method that can be used in solving this problem. The other method that can be used in solving this problem is we can use Henderson Hasselbalch equation. The Henderson Hasselbalch equation. This is how it is. The equation for buffer solutions for weak. Can use this. In this equation, you can easily use we will have a pH like this. The pH will be equals to this is conjugate base divided by weak acid. You can do this. So if we apply this equation, that is method 2. If we apply this equation, we know that the pk, this will be equals to negative log 1.8 1.8 times 10 to the minus 5 plus a log of conjugate base divided by weak acid zero point 0.02 it is minus 4.7444 plus 0.3 0.3 that will be equals to, adding this up will be equals to pH will be equals to, that is 4 minus this plus equals to 5.04. That is the second method. We use this second method here, we'll have the same answer. So that is method 2. This is method 2. This was method 1. This is method 1 here. So that's method 2 in solving the problem. You can solve that problem like that. Then method 2 is that one. Okay. It takes us to question number 2. Question number 2 has to do, has a lot of calculation in it. Question number 2 has to do with the energy cycle, the Born-Haber cycle that is there. The energy cycle below represents the enthalpy changes involved in the formation of solid sodium chloride. Identify the enthalpy changes involved in step A, B, C, and D. Now you have realized that here, this is the initial stage. This is the initial stage here. This is the initial stage here. Here, now it has to undergo step A, step B, step C, step D, and step E. Okay. The question asks, identify enthalpy changes involved in A, B, C. Now, this is sodium. Sodium is solid. Sodium is solid. So in such a situation, there is always atomization. After atomization, for metals, there is atomization. After atomization, there is ionization energy. If there is there is first ionization energy. If there is second ionization energy, it can undergo. Then after that, we now go to atomization of nonmetals. Atomization of nonmetals. After atomization of nonmetals, we now go into what? We now go to the first electron affinity for nonmetals. So in the first case here, this is sodium. Sodium is a metal. The enthalpy change indicated by A is atomization. That is enthalpy change of atomization of sodium. Enthalpy change of atomization of sodium. There is the enthalpy change of atomization. Enthalpy change. Enthalpy change. I said A is enthalpy change of atomization of sodium. B is after atomization. B is the first ionization energy. The first ionization energy. That is B. B is the first ionization energy. That is the first ionization energy. And the C is atomization. Enthalpy change of atomization of chlorine. Enthalpy change of atomization of chlorine. That is C. Enthalpy change of atomization of chlorine. But the other one was sodium. Then D. After the enthalpy change of atomization of chlorine, D is the first electron affinity of chlorine. D is the first electron affinity of chlorine. The first electron affinity of chlorine. That is D. First electron affinity of chlorine. The first electron affinity of chlorine. Then if you were to go to E, the E is the lattice energy of sodium chloride. E is the lattice energy of sodium chloride. Once more, A is the enthalpy change of atomization of sodium. B is the first ionization energy of sodium. C is enthalpy change of atomization of chlorine. D is first ionization energy of chlorine. And the E is the lattice energy of sodium chloride. Okay. Calculate the enthalpy change of formation of sodium chloride. Enthalpy change of formation of sodium chloride. Okay, the enthalpy change of formation of sodium chloride. Okay, once more, you can watch here. Watch here. This is another way of writing the cycle through Hess's law. By Hess's law, you can write the cycle like this. It will enable you to do your calculations. Now, this is sodium chloride. This is sodium atomization. This is atomization of sodium. Atomization of sodium. After atomization of sodium, we go now to the first electron affinity. First ionization energy of sodium. After that, we now go to atomization of chlorine. After that, we now go to the first electron affinity of chlorine. Then this is the lattice energy. So now we can use this cycle. We can use this cycle according to Hess's law to calculate the enthalpy of formation. And in order to calculate the enthalpy of formation, okay, I have drawn this cycle here like this. Use this cycle to calculate it. Now, you see, this is the direct route according to Hess's law, this is the direct route. The direct route is from here to the ions. The indirect route is this one that comes here, right to this level, comes right here, then before coming here, and that is why it is indicated by the dotted line. I've just indicated it by the dotted line that the indirect route is going round before coming here. So if we want to make an equation according to Hess's law, we will say the direct route equals to the indirect route, and the direct route is enthalpy of formation equals to enthalpy 1 plus enthalpy change of the lattice. The direct route will be enthalpy of formation equals to enthalpy 1 and enthalpy 1 plus enthalpy of lattice, enthalpy change of lattice energy. So if we want to solve this equation now, I want to solve this equation here using this. Okay. And the lattice energy, let me say, okay, enthalpy of formation, the direct route is the direct route to the formation of this lattice compound is enthalpy of formation. But the indirect route is going through this route here, from here to this end and back here. And it involves what? This plus this. And this one includes what? This one will involve the enthalpy of atomization, enthalpy, the first ionization energy, enthalpy of atomization of chlorine, and the first electron affinity plus this one. So let's calculate it. Let's see how we can calculate it. So now, enthalpy of formation will be equals to enthalpy 1, enthalpy 1 plus enthalpy of lattice. But enthalpy of lattice enthalpy 1 is equals to what? Enthalpy 1 is enthalpy of atomization, enthalpy of atomization of sodium plus the first ionization energy of sodium plus enthalpy of atomization, of chlorine plus the first electron affinity of chlorine. All this will be equals to what? All this will be equals to plus 10.3 plus 500 plus 121 plus minus 3. Oh, sorry. Plus 364. Altogether, giving me a total of plus 365. 365.3. Now, enthalpy of lattice. Enthalpy of lattice. Enthalpy of lattice is minus 77. Our equation says enthalpy of formation is equals to what? Enthalpy 1 plus enthalpy of lattice. Enthalpy 1 is what? Enthalpy 1 is plus 365.3 plus enthalpy of lattice, minus 776. And what will be our answer? What will be our answer? Our answer will be minus 410.7. That will be our answer. So, calculating this will have minus 410.7 kilojoule per mole using Hess's law. It drives us to the next question. The next question is define the following terms as applied to solid state chemistry. A. Crystal lattice. What is a crystal lattice? This is an example of a crystal lattice. This is an example of crystal lattice. But what is a crystal lattice? A crystal lattice, you can put it in this way. A crystal lattice, this is a regularly repeating arrangement. A regularly repeating arrangement of atoms, molecules, or ions in 3 dimensions throughout the whole crystal structure. Again, this is a regularly repeating arrangement of atoms, molecules, or ions in 3 dimensions throughout the crystal structure. Throughout the whole crystal structure. You can even say it is a 3-dimensional representation of atoms. A 3-dimensional representation of atoms, molecules, ions arranged in a specific order. A 3-dimensional representation of atoms, molecules, or ions arranged in a specific order or pattern. Just as I said the other time, this is a regularly repeating arrangement of atoms, molecules, or ions in 3 dimensions throughout the crystal structure. Or you can say it is a three-dimensional representation of atoms, molecules, ions arranged in a specific order or pattern. Then, what is a unit cell? What is a unit cell? A unit cell. A unit cell is is the smallest repeating unit. A unit cell is the smallest repeating unit of the crystal lattice. Or we can say it is the building block of a crystal lattice. This is the smallest repeating unit of the crystal lattice. In other words, it is the building block of a crystal lattice. That is just all. So you can do it in that order. Then it takes us to give one similarity and one difference between a chemical bond and an intermolecular force. A chemical bond and intermolecular force. A chemical bond. What is the similarity between chemical bond and intermolecular force? The only similarity existing between chemical bond and intermolecular force is that both the chemical bond and the intermolecular force require energy to bind the atoms, the ions, and the molecules together. They require energy. Both the intermolecular force, and the chemical bond, they require energy. They require energy to bind the atoms, the ions, molecules together. So both of them require energy to bind them together. What are their differences? The differences in them is you will notice that chemical bond holds atoms. In chemical bonds, the chemical bonds they hold but atoms, ions. They hold atoms or ions together. Chemical bonds hold but atoms together during a covalent bond or ionic bond. And chemical bonds are stronger than intermolecular forces. Whereas intermolecular forces, they hold but molecules together. Once more, chemical bonds hold atoms or ions together during a covalent or ionic bond. Chemical bonds, they hold atoms or ions together during a covalent bond or ionic bond. And chemical bonds are stronger than intermolecular forces. Whereas intermolecular forces hold molecules together. They hold only molecules together. Another difference is chemical bonds involve the transfer and sharing of electrons. Chemical bonds involve the transfer and the sharing of electrons, whereas intermolecular forces only involve the attraction of molecules to each other. Chemical bonds involves transfer or sharing of electrons, whereas intermolecular forces only involve the attraction of molecules to each other. It takes us to the last section, which is list and locate all the types of bonds in solid ammonium phosphate. The types of bond present in ammonium phosphate. Okay, I can draw, let me draw the bonds in ammonium phosphate. You will see that ammonium phosphate is a molecule that excuse me. Yeah, this is all we have for you. Thank you for watching. Wishing you all the best in your exams. Thank you very much.